Okay, so then you can start.
Yeah, thank you. Thanks for having me. So as Maurizio introduced, I will first discuss some formality of running Axion couplings and discuss the possibility to uncover microscopic origins of Axion by low energy precision physics. So this first part of the talk is based on the work with Kyun and Dr. Hee-jung Kim and Hyun-Suk Chung. Okay, so here I will discuss the classification of possible UV physics for axions, including string theory axions. And we will see that these three different classes of UV physics show clearly different patterns of low axion couplings to the standard model particles at tree level. And it will be also clear that this running effect should be taken into account whether such patterns survives at low energies. So I will discuss the renormalization of axion couplings and then examine this UV characteristic patterns of low energy axion couplings survives at low energies and whether it can be experimentally measurable. Yeah, so we are interested in the axion physics because of the strong CP problem. This page is basically, yeah, for students, but I guess no students we have. Yeah, so, you know, this is basic things. We have this CP violating order parameter in the QC sector, some of the QC setup parameter and a certain phase of the Yukawa coupling matrices. But this CP phase has not been observed, which should be imprinted in the electric dipole moments of fundamental particles like nucleons. And the non-observation of neutron radiant place is stringent bound like 10 to the minus 10. On the other hand, we already know that we have indeed order 1 CP phase in the Yukawa coupling matrices, the CKM phase. So we expect that the CP phase involved in this zeta bar is naturally of order 1. Then this means that we need a serious fine cancellation between these two quantities. And the nice solution was proposed a long time ago that by the fact that the QC vacuum energy is minimized at the CP conserving point. So this is the dilute gas instanton gas approximation of this QC vacuum energy. If presumably the correct ordering of the large value limit of this winding number and space-time volume is taken as discussed in this morning. Yeah, so the idea is to promoting zeta bar to a dynamical field, and then zeta bar will be spontaneously relaxed down to 0. And then it will explain the non-observation of the CP violation in the QC sector. Yeah, so here this scalar field coupled to GG dual operator is the QC axion. And so the most important element of the QC axion Lagrangian is, of course, this axion gluon coupling. But depending on the UV physics for the microscopic origin of this axion field, we may have the other axion couplings to the standard model, the other standard model particles. Yeah, so this is the general form of this QC axion Lagrangian dictated by this global U1 symmetry, usually called the Pechakin symmetry, which is given by the shifter of the axion field in nonlinear realization. And this symmetry, global symmetry, is to be broken by this axion gluon coupling by QC instanton effect. So it gives rise to axion potential and axion mass. And the axion mass is proportional to this axion gluon coupling with known QC parameter like light quark mass and the pion mass and pion decay constant. On the other hand, the axion couplings to the other standard model particles are UV model dependent, and this is the main topic that I will discuss in this talk. If we believe in the existence of the QC axion, then we are also we may be interested in searching for axion-like particle. So they are kind of cousins of the QC axion in the sense that they are theoretically similar in terms of symmetry properties, while they are not necessarily involved in solving this strong CP problem. So their couplings to gluon field can be 0. And actually such particles are ubiquitous in many BSM scenarios. in particular string theory. So the alpha Lagrangian takes the same form as the Q axion dictated by these two symmetries. So it has an approximate shifted symmetry, which is given by the shift of this axion field. And by this, alpha can be naturally light. And secondly, it has a periodicity. And this means that the alpha is a compact field with a certain periodic field length, FA. And this is usually called the decay constant. So FA characterizes typical size of alpha couplings up to this UV-dependent dimensionless coefficient. Yeah, so I will discuss this UV-dependent dimensionless coefficient. So first, we have this KSVZ type model, historically first introduced first for phenomenologically viable QCD model. So they introduce a heavy new fermion charged under this SM gauge groups. So here Axion degree of freedom is identified as phase of a complex scalar field. And bevel of this complex scalar field determines the scale of the Axion decay constant. And in this model, it assumed that this complex scalar field has a coupling, Yukawa coupling to this new fermion. So the fermion, this new fermion obtains mass from the Pecha-Eichen symmetry breaking, spontaneous Pecha-Eichen symmetry breaking, and its mass is to be around the Axion decay constant up to this dimensionless Yukawa coupling. And so the associated Yuon Pecha-Eichen symmetry is given by this linear transformation of the involved field. And the key feature of this type of model is that none of SM fields are charged under this linearly realized Yuon Pecha-Eichen symmetry. And this is an important consequence for the low energy pattern of Axion couplings. So in order to obtain a low energy effective Axion Lagrangian, it is convenient to go to field basis where this Yuon Pecha-Eichen symmetry is non-linearly realized by shift of the Axion field alone. And this can be done by redefining the involved fermion field by this Axion-dependent field redefinition, whose exponential argument is proportional to their Pecha-Eichen charge. And then in this redefined field basis, this quark field, this new fermion field becomes singlet under Yuon Pecha-Eichen symmetry. And the Yuon Pecha-Eichen symmetry is non-linearly realized by the shift of the Axion field alone. So in this field basis, this Axion couplings to this fermion field has to be given by derivative of the Axion field. And because this field redefinition is chiral, by the chiral anomaly, Axion has to couple to gauge fields. And then below this exotic heavy fermion mass scale, this derivative coupling is simply integrated out, leaving nothing, suppressed by this low energy momentum scale over this heavy fermion mass scale. So we end up with this Axion couplings to the gauge fields only, the leading order. Yeah, so, and this is actually direct consequence of we have none of the standard model fields are charged under this linearly realized Yuon Pecha-Eichen symmetry. Yeah, so we may classify this type of UV physics as KSVZ-like models, which are characterized by vanishing two-level couplings to the standard model fermions. Okay. And secondly, we have this Dine-Fischler-Srednicki type model. And here, in the original DFSD model, they assume that the Axion couples to the standard model sector at tree level through this Higgs-Porter coupling. So again, here Axion degree of freedom is identified as the phase of a complex scalar field, and this complex scalar field couples to the SM sector through this Higgs bilinear operator. Yeah, so this model is basically based on this 2XWM model. And then point of important feature of this model is that because Higgs field is has to be charged under linearly realized ion Petrarchan symmetry for this operator to be invariant. That means that by this Yukawa coupling, some of the SN fermions must be charged under ion PQ. Actually, there are multiple ways of assigning Petrarchan charge for this Lagrange to be invariant under associated ion Petrarchan symmetry. But yeah, their physical consequence should be same. And for simplicity, we may consider a simple charge assignment where only this down type Higgs is charged under ion PQ. Then by this down type Yukawa couplings and lepton coupling, down cock or lepton field must be charged under ion Petrarchan symmetry. And in order to get the low energy effective action, we again go to a field basis where ion Petrarchan symmetry is non-linearly realized by the shift of the Axion field alone. And this can be again done by this Axion dependent field redefinition with this exponential argument proportional to the Petrarchan charge of the associated field. And then in this basis, we get Axion derivative couplings to this originally PQ charged field. And now they become, of course, a PQ singlet. And because this transformation is chiral, again, by the chiral anomaly, we obtain the Axion couplings to the gauge fields. And below the electric weak scale, actually, there is an important threshold correction here. So this Axion couplings to the Higgs field gives rise to the Axion Z-boson kinetic mixing. And after integrating out Z-boson field, actually this gives rise to sizable correction to the Axion couplings to standard model fermion field, depending on the ratio of this Higgs path, usually denoted by tangent beta. Actually, this process of integrating out Z-boson is equivalent to finding physical Axion direction after eliminating this Goldstone boson direction of the electric symmetry breaking. Yeah, so then we obtain this tangent beta dependent. We end up with this tangent beta dependent Axion couplings to the standard fermions. And this is the direct consequence that in the UV model, some of the SN fermions must be charged under this linearly realized ion Petrarchan symmetry. So we would classify this class of UV physics as DFS-like model, which are characterized by order 1 level couplings to the standard model fermions. And the third distinctive and important classes of UV physics is the string theoretic model. So here, the 4-dimensional axion is no longer identified as a phase degree of freedom of a complex scalar field, but here rather, 4-dimensional axion can be identified as zero mode of a higher dimensional p-form gauge field. So in string theory, we have XR dimensions, and string theory predicts many kinds of higher dimensional higher dimensional form field with p indices. So the anti-symmetric tensor field with p indices is called the p-form gauge field here. And higher dimensional component of this p-form gauge field looks like a 4-dimensional pseudoscalar. And moreover, if this gauge field has a certain configuration called harmonic p-form over this XR dimensional space, then the corresponding 4-dimensional degree of freedom is approximately massless. So it can be naturally identified as a light pseudoscalar 4-dimensional axion. So if we consider SUSY preserving compactification, then the low energy effective Lagrangian for axion will be described by this axion chiral superfield with associated superpartner field tau, the C-axion field, and this is identified as volume modulus of p cycle due to this harmonic p form. And this means that this tau parameterize the size of the volume where this p form gauge field lives, XR dimensional volume. And associated Yuan-Pechakin symmetry is understood as a remnant of a higher dimensional gauge symmetry of this p-form gauge field. Yeah, so this is an eccentric symmetry inherited from gauge symmetry of string theory. And then the four-dimensional low energy effective action will be described by the four-dimensional supergravity with the Keller potential and the gauge kinetic function, and dictated by this Yuan-Pechakin symmetry. This Keller function must be a function of t plus t star, the complex conjugate of this axion chiral superfield, and the gauge kinetic function should be proportional to this axion chiral superfield because of the gauge symmetry or this eccentric Yuan-Pechakin symmetry. And here phi I denotes metal chiral superfield. And you know, the four-dimensional field in XR-dimensional theory, the wave function normalization of four-dimensional field is generally depends on the volume and the shape of the XR dimensions. So it can have a certain dependence on this axion chiral superfield via this volume modulus, and the wave function dependence on the volume modulus of P cycle. And these people show that if we consider large XR dimensional volume limit, then the wave function dependence is insensitive to the shape of the XR dimensions. And it's more or less given by this simple scaling of the size of the XR dimensions. So yeah, generally if we consider a simple large volume limit, then this wave function normalization will take this form with a certain scaling weight of the associated meta field. And we can write down this superfield Lagrangian in terms of component field. Then this K0 term will give rise to this axion kinetic term. And this term will give rise to the axion derivative couplings to the metal fields. And the gauge kinetic function, the real part of the gauge kinetic function gives rise to this kinetic term for the gauge field. And the imaginary part gives rise to the axion couplings to the FF dual term. And here the web of the C-axion field is identified as the gauge coupling of the associated gauge field. So for standard model gauge field, this should be over order 1. And this scaling weight and the CA are generally of order 1 in string theory. So the associated dimensionless parameters here are all order 1. Yeah, but this dimensionless parameter can be depending on the size of XR dimensions. This can be parametrically smaller than order 1. But yeah, except this here, the involved parameters are all of the involved parameters are order 1. Actually, in this field basis, axion is dimensionless field variable. And then here we see that the axion couplings to the metal fields and gauge fields are given by this order 1 coefficient. So this means that string theory axion couplings to metal fields and gauge fields are comparable to each other, both arising from this T-level interaction. This means that if we go to this canonical normalization of the axion field with the identification of the axion decay constant given by this quantity, then axion gauge field coupling is given by this standard normalization for axion gauge field coupling with this one loop factor. And because this axion metal coupling should be comparable to this axion gauge field coupling in this basis, so in this canonical field basis, the axion metal coupling turns out to be suppressed by the same one loop factor. Yeah, so this is the characteristic feature of string theory axions. So as I mentioned, if this is order 1, without assuming the parametrically large axion dimensional volume, then the typically string theoretic axion decay constant will be given by the one factor times Planck scale, Gauss scale. However, if you consider some large axion dimensional volume, then this can be parametrically smaller. Then we can get a parametrically small axion decay constant in string theory as well. Okay, so this shows the comparison of T-level axion couplings to the standard fermion. So we normalize axion photon coupling with this one factor for comparison. And in this standard normalization, this axion couplings to the fermion field, generally for DFS-like models, it takes order 1 value, and case physics-like model, it is 0. And for string theoretic model, it is given by this one given in this one loop order. So at tree level, those 3 classes of high energy physics show clearly different patterns that they may be distinguished by this precision measurements. However, because this it involves this one loop factor, the relative correction have to be carefully examined whether such patterns remains in at low energies after renormalization of axion couplings. So we studied this running of axion couplings. Okay, now let me discuss this. So at leading order, at one loop order, axion couplings can be renormalized by Yukawa interaction. And the dominant contribution comes from this top Yukawa coupling. Then axion couplings to this third generation quarks and up-type Higgs are renormalized by these RG equations. And here we parameterize this RG coefficient by NT-parameter. NT-parameter is defined as the sum of the axion couplings to this involved field. So for case video-like models, by definition, this is 0 because none of this field is charged under linearly realized Yuan-Pechakin symmetry. So this is identified as sum of the Pechakin symmetry of the involved field in the basis where Pechakin symmetry is linearly realized. On the other hand, for DFS-like models, this can be generally of order 1 from the scale of FA, where this axion degree of freedom appears. However, in the original DFS model, actually this sum should vanish because this should be invariant under Yuan-Pechakin symmetry. So this coupling, this quantity becomes non-zero when this heavy Higgs degree of freedom is integrated out. Because then this standard model Higgs, the corresponding Pechakin charge is different from this up-type Higgs Pechakin charge. So in the original DFS model, the one loop learning takes place. Below the scale of this heavy, the mass scale of the heavy Higgs, charged Higgs mass. Because at one loop level, for case video-like model, this renormalization doesn't happen. So we have to consider two loop level also. And at two loop level, axion couplings can be renormalized by these diagrams from this axion gauge field interaction and also axion fermion coupling as well. So the RG coefficient is proportional to this CA tilde parameter defined as the sum of this axion gauge boson coupling and axion fermion couplings appearing in this loop. So for field theoretic axions, like the case-Vizil type model or TFS type model, because this chiral anomaly coefficient has to be the same as the axion fermion, that has to be given by the sum of the associated Pechakin charged fermion field. This vanishes at the scale of FA, and this becomes non-zero when the heaviest Pechakin charged fermion is integrated out. So for field theoretic axions, this axion coupling running starts below the scale that is heaviest PQ charged fermion. On the other hand, for string theory axions, from the string scale, we may have this non-vanishing coupling, and the axion couplings start to run from the string scale. Yeah, so to give you an idea, this is a numerical result. So this shows the low energy axion couplings to U quark and D quark and electrons in terms of the involved in terms of the UV parameter, the tree-level value, after this renormalization of axion couplings. So here MPSM means the scale where the running of the axion coupling starts, which is taken to be here 10 to the 10 GeV. And for to cover DFSC model, we take this tan beta parameter to be 10. Yeah, then this corresponds to the one-Louvre contribution. Yeah, so this should be given by this NT times logarithm factor times one factor. Yeah, so it agrees with this naive expectation. And this contribution from this two-Louvre contribution arising from these diagrams. And then depending on the associated gauge couplings, the size is from 10 to the minus 4 to 10 to the minus 2. And it agrees well with this naive expectation. But there is a peculiar value here. Because electron is colorless, it cannot be understood as this diagram. But the size of this contribution from axion gluon coupling is quite large compared to this contribution from this other electric gauge boson field. Actually, this contribution is from this three-loop diagram. So axion gluon coupling renormalizes the axion top coupling, and this axion top coupling in turn renormalizes the axion Higgs coupling, and then after Z boson is integrated out, it gives rise to the axion electron coupling. Actually, previously, it was thought that the leading contribution to the axion electron coupling will be given by this axion couplings to the electric gauge field if they are present, or otherwise it will be given by this axion pion mixing from axion gluon coupling. However, numerically it turns out that this three-loop contribution is bigger than this two contributions. And this can be understood because it involves, here this is bad, okay? How can I, sorry. Right, yeah. So it involves this strong gauge coupling and tam yuka coupling that is order 1. So even if it is suppressed by this three-loop factor, because the associated gauge coupling is and the tam yuka coupling are large, so numerically it turns out that it's 2 factor larger than this electric gauge field contribution. And this can be important for string theory axion, as I will show soon. Yeah, so this RG correction can be parameterized by this R parameter, which Maurizio will discuss later, which depends on the scale where this running of the axion coupling starts. And this actually R parameter is quite insensitive when we take the BSM scale from is above 10 to 7 GeV. However, this can be much smaller for BSM scale around 1 TeV, because you see here this one-loop contribution is terminated at the TAM-mass scale. Okay, so in summary, the situation is like this. For DFSC-like model, this axion fermion coupling is larger than axion gauge field coupling. In the case-like model, the situation is opposite. And for string theoretic models, they are supposed to be comparable. So in principle, by measuring the ratio of Axion fermion coupling to Axion gauge field coupling, we can tell, experimentally tell, which kind of UV physics is there. But most of the Axion experiment is performed below the QC scale. Eventually, you have to consider Axion couplings to the neutron and proton and electron below this QC scale. And they can be computed by this matching scale at QC scale 1 GeV. First of all, Axion photon coupling is simply given by this sum of Axion couplings to the electric gauge bosons. And this contribution is from Axion gluon coupling arising from Axion pion mixing. And here, this part, the Axion proton coupling is matched to the Axion couplings to quarks and gluon. And here, delta U means the matrix element of this UCO component inside the proton, and delta D is the DCO component inside proton. Yeah, then numerically we have this relation. And compared to this Axion proton case, in Axion neutron case, you see that this gluonic contribution is an order of magnitude smaller. And this is because that this UCO component inside the proton is approximately 2 times larger than the DCO component, while the sign is opposite. While we know that this DCO mass is about 2 times larger than mu, so yeah, there are some cancellation, and we get an order of magnitude smaller value for this gluonic contribution to the neutron coupling. Again, to give you idea, so we take this example for parameter point. Then for the DFS-like model, assuming that we have T-level order 1 T-level couplings to the standard model fermions, they are all supposed to be over order 1. But Maurizio will discuss that this T-level coupling is suppressed by some large tangent beta ratio later, and then this one loop correction can be important. And for the case of this is a contribution from gluon coupling, and for case like model, the leading contribution from this two-loop level diagrams, and so we have this radiated correction. And for string theoretic model, we have this one-loop contribution, one-loop level T-level contribution, but with one loop order. So yeah, this gives rise to those contributions. Here for Axion electron coupling, this is contribution from the Axion gauge boson interaction, and this is a contribution from the T-level Axion electron coupling exists in string theory. Actually, so numerically they can be quite comparable because this gluon coupling is quite large. So to determine their predicted psi, actually this relative sign is important. And here this omega I is positive. And in principle, this sign should be determined by theory, but there is this sign determination is quite a subtle issue. But yeah, we do our best and we find that this is plus. But if this is minus, then there will be cancellation between this loop contribution and the T-level contribution. And string theoretic prediction can be as small as k-space like this. In this case, it will be difficult to distinguish between two. However, yeah, fortunately, if this sign is correct, then yeah, we get this result. First, we consider the QCD Axion case, characterized by non-vanishing Axion gluon coupling. Then, because Axion proton coupling is dominated by Axion gluon coupling, it cannot be used as a discriminator. So it shows the this value regardless of the class of models. But in the case of axion neutron coupling, because this gluonic contribution is order of magnitude smaller, we can discriminate DFSE from the other type of UV physics. But to completely determine, distinguish among these three classes of UV physics, we have to look at axion electron coupling. And if the relative sign is positive, then we have this gap. But if the opposite sign is correct, then this gap should be shrinked, and it will be difficult to distinguish the string theory models. But at our best, we believe that this result is correct. And for the case of axion-like particles without gluon couplings, then the situation is much more promising. In this case, even this axion proton coupling can be used to distinguish among these three classes of UV physics. So this left-handed plot is the case where this ALP couples to the SU2 gauge field only, and the right-hand side is a case where axion couples to the UNI hypercharge gauge field only. So in summary, axions are theoretically very motivated new particles, which maybe gives us important clue for underlying UV physics when they are discovered. And in principle, we have these three possible classes of UV physics, showing clearly different patterns of axion couplings to SM particles at tree level. But the renormalization of axion couplings should be carefully taken into account. And after that, we find that as for Q-set axion, it may be challenging to discriminate the string theory models from the case-visit-like models, if not impossible. And for this axion electron coupling plays an important role. On the other hand, ARPs without gluon coupling, it is much more promising to distinguish among the three classes of models by various precision measurement of low-energy axion couplings. Okay, that's the end of my part, and I will. I continue this. If there are no urgent points to discuss, maybe I'll just take over, and then at the end we discuss it. So maybe that's to let you too sleepy for my part. But then okay, next one, get these, and then we can continue like the discussion at the end. I probably don't need this, but I think for okay, let me send this here. So what? Okay, after this introduction, now what I'm going to do? First, I grab this. I'm going to need it. So what I'm going to do is discuss a little bit of what could be the phenomenological implication, and I take the DFSE axion. So the axion, right? So the first thing I want to do is simplify considerably the discussion. This was a very general discussion, many different models, all the corrections. But in the end, what I want to show is that we understand what are the leading contributions. And then we want to focus on the leading contributions to study the phenomenology, what could be essentially detected, or what kind of effects we could see. And some are large. So that's an interesting thing, okay? So, and this is, actually, by the way, this is the fruit of many discussions with Enrico Nardi and Shohei Okawa, and then we were here. But then also with Luca Di Luzio, Federico, Gioacchino will be here later. These weeks, okay. But so let's move. So as I promised, I want to simplify things. So the leading. So this is repetitive. This was already in Sengui slides, but essentially the leading contributions to the change of the couplings comes from the Yukawa top. So we can write this an equation like this, which has the coupling at low energy, right? And this is what we measure. So when we do an experiment or we do phenomenology, we measure this, and this could be the up or the down. In fact, what we measure is actually the coupling to the nucleons. But then we know how to get those, right? We can read the paper by Grilli di Cortona, and you know, so we know how to go to from this to the coupling to nucleons, and right. But then so this is equal to a coupling at some high energy scale. This is the Pechi-Quinn constant,
all right? And these, we know how to write this down. We know how to write this down, right? We know that they can be expressed in terms of tangent beta, which this was all introduced in the previous talk, but I repeat, like I wanted to repeat, right? To summarize, right? So we know how to write this in terms of this tangent beta, which is defined this way. I think Andreas is happy about my convention here. And these couplings are standard. So this we know, and we know this obviously is the top, right? And then, but then there is also another term, right? So we have this that we know how to write down, and then we have this part, and this part is a correction that depends on the I energy and can be factorized, right? In a term, this is the leading contribution. I just write the leading contribution here, okay? And then multiplied by a factor, which is what Stengui was showing, and this factor depends on an unknown scale, which is not the page-queen scale necessarily. It's an unknown scale which tell us from where we should start the running, essentially. Okay, so and this depends from the fact that these models, these Axion models, are necessarily extension of the standard model. So you have maybe another Higgs, right? So in the DFSZ2, this would be essentially the mass of the second Higgs when this would be integrated out. So there is an extra parameter, and when there is an extra parameter, there are like, you know, extra uncertainties. So that's the key, okay? And these, what's interesting is that this correction may be significant, 100%. Could be like, you know, just as big as the initial one. So it's not necessarily small. Obviously, this depends on the scale, which we don't know, and also on tangent beta, which is here. Okay, so there could be even qualitative changes for this correction, right? For example, it could happen that this is 0. Think of the coupling to electrons in the DFSZ model, right? At small tangent beta is 0. It's proportional to sine square beta, no? And then, but then maybe this could be finite. This is an important point for example, reviewing the RGB bound that Oscar discussed in his talk, as I'll show, because that depends on the electron coupling, right? So there could be even qualitative changes. So this is a fairly a large effect. Okay, so in general, we have the consequence, fundamental consequence is that since this is large, we have unavoidable additional uncertainties because we don't know the scale. But also there are some general results, and I want to somehow try to present some of the general results and also some of the uncertainties, of course. Okay. All right. So this will be probably short. I hope. I know it's getting late, but so first of all, in the spirit of simplification as much as possible, because remember, I have in mind phenomenology, and phenomenology worries only about large things, right? The largest possible. So we can actually express this. This can be expressed in terms of two combinations. Well, really, yeah. Okay. So we have a psi. Remember, can be up, down, or electron. So we can get the isoscalar or isovector combination of these two, up minus down and up plus down, and then we actually have an analytical fit. This is an analytical fit which is good at the level of 3% probably, 2%, right? So it's quite a good fit. This X is the scale of the physics beyond the standard model. So we can express this. And why do we break this in this form? Because we realized, and this can be understood from a theoretical point of view, right? We realized that one of the two is large and one of the two is very small. And in fact, the top one is large. This order 1. It depends obviously on this, right? But this is a large, right? And this is half of that, so it's also large. Coupling to the electron, the correction to the electron is also large. But this one, the isoscalar is instead small, right? This is a 10 to the negative 4. This is about 1,000 times smaller than that, and so I don't care about it. We'll throw it away. Okay, actually I'll show some plots, and the plots are numerical, and they include also these, right? Because Shoei did calculations with everything, and when I did the plot, I don't care. I showed everything, but I know that this will be the leading effect, right? And so this is very simple, right? We have this correction, very simple, and almost anything can be done analytical, except for some places where it gets big, the correction, then you cannot really propagate too much. But in general, most of these things we can do analytically, right? So now I go to the DFSE, and I'm able to calculate all these couplings, right? C0, C3, this is the scalar, C3 is the isovector. By the way, this is a proton and neutron, but we know how to connect a P and up and down, right? This we know how to do. In fact, he showed the relations, right? So, but I can calculate these couplings, right? For the DFSE, all analytically in terms of this function, right? That I showed before. Everything is analytical. The corrections and the coupling, everything is analytical. And now, if you do plot them as a function of tangent beta, this is what you get, ignoring this RG corrections, and this is what you get adding the RG corrections. So you get an uncertainty. So first of all, these two are not even compatible. Every effect is large as small tangent beta. And this is one of the general result. This is one of the general results I was talking about, right? Because every change is proportional to delta C3, every change. And delta C3 is proportional to the cosine square of beta. So a large tangent beta fails. In fact, if you go to very large, it's something we discovered just today with Shoaib, but if you go to very large tangent beta, then maybe you need to add the bottom, but the correction will be still very small, like tiny. I don't care about it. Yeah. Yes, there is the mass of the second Higgs. It's some of a combination that you can probably ask this combination. You generally identifiable at the So the lower bound is experimental essentially, and the upper bound is called for 1 TeV to 10 to 9. Well, here to 10 to 9 GeV, but in general it would be to FA. When we do plots where there is FA, we don't go over FA for consistency. So, okay, good. So, all right, let me show some. I mean, there's not much more, but let me show just some results. This, as I say, the corrections are larger as small tangent beta. So now let's talk about some of the results that were discussed earlier, right? So last week Oscar presented this RGB bound. All right, so these are stars. RGB are stars, and if you look at the most luminous stars in this branch, which is an evolutionary stage, this luminosity depends on new physics, so you can use that to set a bound on new physics. And this is a very strong bound, by the way. It's the strongest on the coupling to electrons. And I just simplified what Oscar, the bound that Oscar gave, can be written in this way in terms of the mass of the axion mass, and the CE. Remember, CE, we know what it is 1/3 sine square beta, right? So I can immediately draw this line here, and that's what I get. That's what I get. I have to say I'm using the bound that's published, not the latest that he showed, which is slightly stronger. So right, so this may be slightly less, but for the purpose of presenting, I didn't want to redo the figure and everything. But okay, so but look what happens here. This is one of the most interesting results. So if you go to tangent beta very small, then you have no bound from RGB, because RGB measures the coupling to electrons. Okay, but what we're saying is that since there are unavoidable corrections for the FSE, the minimum you get is this, which is fairly big. This 0.1 EV is an important number for cosmology, for example, right? For hot dark matter. So you get a bound. Yes. Yeah. Okay. So we're changing. Okay. So in this case, I'm changing the scale of this new physics scale beyond the standard model from 1 TeV, which is close to the experimental bound, say, to FA. So this changes, this thing changes from FA. At each FA is recalculated, right? So it's never larger than FA. So that's the width. So you can get a bound which is this large, but the minimum of this. So now you can't forget RGB by saying, oh, maybe, you know, we are a small tangent beta, who cares about red giants? So okay, so then this is maybe a little bit negative for experimentalists. So, maybe they are worried about the RGB bound, but there is also something interesting, no? From the fact that now I'm saying, yes, please. Okay, remember that R includes, depends very strongly on the coupling to photons also, which is not renormalized. So I think, so essentially, if I want to think about GIE, I can think of the R parameter, but that's not very efficient way to measure it. Or I can think about white dwarfs, or I can think about red giants. And red giants is the best, so that's what I look at. Connect GA gamma with GAE. Well, I didn't do it. I don't know what I get, but I didn't do it, right? So, but yeah, something one can look, right? This is somehow, yeah. So now we think about the sun, Sebastian, right? You're interested in the sun, and now we're saying even if I take the DFSZ. There's going to be a larger flux from the sun than I expected, because before I could say, oh, maybe there is DFSZ, maybe tangent beta is small, and so I need to worry only about these axions that are produced through the axion photon coupling from the sun. But now I say, hey, look, no, there is necessarily an additional contributions from the coupling to electrons that cannot be cancelled, and this means that the flux is larger. So the flux from the sun of the DFSZ is necessarily larger than previously calculated. How much larger? Well, these calculations can be done almost entirely analytically, right? But so how much larger? Not very much. But somewhat. But it could be also very large. So if I look now at experiments that look at the sun to detect axions, for example, YAXO, right? This is YAXO, and baby YAXO. So this is an experiment that will be hopefully started very soon in DAISY, right? So this is the sensitivity to the DFSZ axions that's been calculated so far, and here we have how much more sensitive could be. It's almost get to the, if you think that here there is some unitarity bound, it really explores the whole tangent beta region, right? So allowed by unitarity, for example, by perturbative unitarity, right? So this is substantial change. And for YAXO also this, for YAXO you enlarge even the region that you detect even without any tangent theta. So somehow this is a positive result, and it's due to the fact that the flux from the sun is just larger than expected. And then we know from Javier Redondo and Sebastian as well, right? The photons from the sun, right? You can get a lot from this flux, right? So it's very interesting. And then obviously you can do the same with other experiments like Xenon or LUX or LZ, right? That look at the sun as well, and also in this case maybe their potential is larger than they expected, even though in this case they're still a little bit far from the region. As Oscar showed, right? You know, maybe it's a little bit difficult for them to go beyond the RG bound. Then, okay, to connect to Giuseppe's talk, because he also gave a talk, so I didn't want to disappoint him. So I presented also the bound from supernova. The bound from supernova depends on the coupling to nucleons, and according to the latest a paper which actually came out yesterday, the revision with this formula. It's not quite this formula, but it's this formula essentially, right? So the supernova, the axions is produced in a supernova with this kind of coupling, effective coupling. And this depends on C0, which we know is not corrected, and then on C3, which instead is corrected. And so we get that the supernova bound is this. Obviously, a large tangent beta, nothing changes, but a low tangent beta, it gets a little bigger. So it's not as, this effect is not as astonishing, you know, like big like for the electron, because it's not quite corrected so much. But I want to say that before, like in the previous years, where people were ignoring the pion contribution to supernova, if you use only Bremsstrahlung, this is almost not corrected at all. But now when you add pions are coupled to C3 through C3, and so they add. So this change that we see is almost entirely due to the contribution of the pions. Right, the Bremsstrahlung, not very much. In fact, if you think about it, it's a way. This is uncertainty, right? When we do measurements from low energy. So at one point, if we consider only Bremsstrahlung, the uncertainty would be less. In this case, it's more because the pions contribute, right? And so just to show you, I think one last slide is the case of a hot dark matter bound. And I know that in this room there are many experts that are currently working on hot dark matter bound. So this is just you know, like a very basic example with instantaneous decoupling and everything, right? But even in this case, you have actually that the bound is a bit stronger, and this is because the coupling to pions is a bit stronger. This could have like my 2 cents about this. Right? I'm not an expert on this, but my 2 cents is careful, because now if you go to low tangent beta, you may have thought that the coupling to pions is not very important, and now we're saying, well, it can be still be important. For example, Alessia, I think you wrote, like in your paper with Rompineve, no? It was also here, right? I think you wrote that maybe then when yeah, sorry, I didn't meet you yet. But you know, like maybe you need to rely on coupling to leptons or something, because the low tangent beta this may be negligible, the coupling to pions, but now we're saying, well, it's not so negligible, so maybe this should be reconsidered, and they didn't reconsider it, so I don't know if it's negligible or not, but it could be. Okay, so and with this I close, and so I close by saying that essentially this is an age of Axion detection. I think Axion, we could detect the Axion. I mean, it's a possibility that's not that far, that strange possibility, and so I think it's important to study possible implications of, like, you know, these corrections. We have to do a little bit more precise calculations about these things. And thank you very much. And now, if you have some questions for all of us. No, but you mean for hot dark matter? No, what? For the case that tan beta is 0.1. Oh. Yeah. There is a tan beta 0.1 is actually below the unitarity bound, which is about 0.3, I think, 0.28 or something. No. Yeah, but here I'm scanning tangent beta, no? This tangent beta. So I'm not fixing tangent beta. I don't know if you understood it. For the small tangent beta, 0.4. Yeah. No, for first time
heard about the coupling, Axion coupling, and I learned in some paper point power. I was confused. I said, what? The coupling is a charge because you have the linear and then some exponent, you will define the field, but then exponent as a charge. You define the field that then in turn spits out that charge. Charge, no. And so I was very confused. I remember a long conversation with Luca Di Lì, where I was saying, listen, if I start from a theory which is non-anomalous, I run the charges, I get an anomalous theory with this technology. You understand? Because if you modify the charge in surrounding, the anomaly freedom, solution changes. I was wrong. And the fact is that until you are in the 2D double mode, what I say is true. You don't renormalize. The capsules do not run because they are charges. But once you go to the standard model limit of bar light X, then of course the charge is no more defined.
Yes.
Because the X is overlapped. And then
you start running it.
I would like to formalize this argument because I didn't have the time or didn't have to formalize. But the real point is that if you take the scale that Maurizio goes beyond the standard model at FA, then you have all the running, because you are immediately in the standard model.
Yeah.
And then the coupling run. But if I take the scale
Down.
as 1 kV or 150 if possible, then I can immediately pick that model. The charges are well defined, they do not apply. That's why it's bad. I just my question. So, something I think at some point we should say in a very correct
Clear,
way,
yeah.
But it's very nice.
Very easy to get confused. Yes.
It's very nice because I say it wasn't on.
Please, yeah. Yeah. Yeah.
This is actually how the like 1 kV. So if you assume
Yeah.
let's say
You have to be careful with the unitarity bounds. You would. One. I don't know if it's so big, but Shoei has been is been worried about this. Yeah. So 0.7 is large because you see essentially you could be very close to the standard. No. This is numerical. The plot is numerical. I can do a lot of this and get close results analytically because the formulas are easy. But this includes these plots include also R0. The unitarity bound also, like for me, it's somewhat less important, right? It's more like okay. Should be cut at the unit, at least show the unitarity limit. which is something we've been thinking. Yeah. Yeah. Okay. So they both saying essentially you may enter in a region where it's not justified anymore to assume smaller couplings, right?
Well, I have to say that the unitary bound that we are using are not from the absence of line of force, but from unitarity of a scattering of force. And this has been computed by Maurizio, so he knows the details, and but he knows a lot about this unitarity bound of a scattering. I believe because Luca claimed that they are stronger than
the absence of the Landau loop.
So, but I don't know the details. The details are next week.
Yeah.
But it depends if you keep being in the two standard model, or if you go into the coupling regime, where you have just the single piece, and then the top Yukawa coupling is divided by the sine.
Yeah.
Well, it's not the original top Yukawa coupling that couples to a chart. Is the Yukawa coupling
Divided by
the
the
top to the standard model, and this is a difference. So things change. But the paper will be out soon. It should have been out the past week. And then
yeah. All right. So more. Yeah, please. Yeah.
Because there is also a way of talking. No, at some point, Maurizio say, well, the flux of the sun in Axion is larger, which is doesn't match my view. My view is that the flux from the sun is what it is, but you move in different regions in the parameter space, MA.
Yeah.
So you don't have to. I mean, of course, if you fix a point in parameter space, then it's correct to say the flux is large. But I think that you have a limit. In fact, you measure a limit of the flux.
Well, we didn't measure it. We didn't measure it. I wish we had.
You measure a limit.
Somehow, what I'm saying is,
and then you have to translate this limit into parameter space.
Yeah.
According to use level result.
Obviously,
correct.
If you express the flux in terms of the coupling like G gamma and GE, it doesn't change, of course. Only when you look at the FSZ changes because of the way you number of events. But the sensitivity,
the power.
Yeah. But somehow plots like this, plots like this. Oops, sorry. Where am I going here? This, like a plot like this, was incorrect. So somehow a plot like this is what's shown in the literature, and I'm saying, well, this actually the sensitivity is actually more. So when I say the flux is larger, it's very clear message, very easy to understand. But obviously we're talking about GAE is fixed, so and G gamma is fixed. I'm just saying that GAE is not zero. It cannot be zero for the FSZ, right? So there is that contribution, right? So yeah, language is a little bit. But yeah, your question, please. Yeah. 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 This is one of the issue, reconstructing the high energy scale. it's more complicated. I mean, you'd have to do. Right, you mean it'd be more likely, maybe if you, I don't know, like you want to do, because you also don't know tangent beta immediately, right? So I'm just saying there is more chance that you get it if it's the FSE, but then reconstruction will be more difficult. Like I don't know, you have to do maybe multiple experiments or something. I don't know, because there is this you don't know, right? Yeah. Yeah, maybe if you have enough energy resolution to understand what's coupling to the photons, and you think this is TFSZ, then I can find tangent beta somehow from the different couplings. But then and then maybe with some work, I don't know, you can reconstruct the UV, but there is an additional uncertainty. What I'm saying. No, I know that paper. I know that paper of yours. But now I'm saying, now I'm saying, which is a beautiful paper, which I always refer to, with Jorgen Lennart and then Sebastian. But now I'm saying for the FSE there is an additional parameter, and this is not a new theory. This is the DFSE. It's just that it's unavoidable somehow. Yeah, Johnny. Yes. No. Yeah. Yeah. To go back to the no running, essentially. No, Shoei is I close to the heat. Right.
No, that's clear. That when you go to metallic bound,
Then you cannot do calculations anymore, of course. Yeah. Yeah. So maybe.
No, I think but it's also very unnatural. Set of couplings. These are large values. The coupling is really large. And one is very large, the other is very small. But yes, you're right.
Yes, Oscar. Yeah.
Concerning the comment by Enrico, the fact that you are changing the position in parameter space, what you need, this may have an effect on the X-ray spectra observed.
No. But X-ray spec, but oh, I don't. I don't think so, right? No, I mean the flux, because when you write it in terms of GA gamma GAE. I mean, if I plot the flux as a function of the energy, right, the spectrum. I mean, depends. I need to fix normally I fix GA gamma and GAE when I do that, right? So then this is cancelled completely. If I want to do that spectrum fixing MA and tangent beta, then maybe, but nobody does that somehow, right? You do the spectrum, you fix the couplings, and I don't know. I mean, I don't know if it's depends probably what variables you use. But remember that if you express your quantities in terms of GA gamma and GAE, like coupling to electrons and to photons, in general, nothing changes, right? This is then it's model independent. Yeah.
The coupling to the photon doesn't run.
Yeah.
So what you have the effect that you only do the production
To electrons, right?
So while when you are the supernova, then there's a nuclear coupling is what determines
Yes, right.
how far to drain energy. But in this case, the effect is just of GAE, the production, but not
G gamma is
GAE.
yeah, right. G doesn't. But the spectrum depends also on GAE though, right? Yeah, but only that part would be yeah. But we still pick the 1 keV, and that's what I'm saying, right? You know, we still pick the 1 keV, the GAE, and the 4 keV, the G gamma, and that wouldn't change. Yeah, it's not changing. There is not a change to that kind.
So if there are no other questions,
All right, thank you.